So the question is, can fluctuations in alpha be effective as a dynamo mechanism? So let me just, we've written down here that, oh God, it's in the wrong colour again, isn't it? All you have here, we don't need to read this. This is just an axisymmetric set of equations representing the usual sort of alpha omega or alpha squared dynamo model. The new term is here, you can see it, amidst the gloom, alpha 1b, all the rest is a standard part, and then you have the term in alpha, which in principle can sustain the toroidal field, but of course normally one thinks about this term here, the differential rotation term, as sustaining the toroidal field. And some people have looked at fluctuations before. Krejcinen, a long time ago, considered an alpha squared dynamo with this term absent, but including both these terms, and looked at alpha as a random function using first order smoothing, a simple approximation, to find the average fluctuating fields due to this fluctuation in alpha. And what he got was a sort of modified diffusion term. It was suggested that you could produce dynamo action if these fluctuations were sufficiently vigorous. But the difficulty was that in order to get this term to operate properly, the scale of the fluctuations in alpha in space was similar to the large-scale fluctuations that you were trying to make much longer. So the theory sort of broke down just when it was getting interesting. So it's fair to say I think this was an inconclusive piece of work. Then more recently, Brandenburg and Vishniak, there are a lot of people here who've done something here, so if I've misrepresented them, you can beat me later. Just let me get through the talk before you. Brandenburg and Vishniak and Sokolov and Fedotov, there are three different works here, looked at alpha-omega dynamos for galactic fields, but in a reduced form, principally. So looking at these equations, but reduced essentially to a set of ODEs with fluctuating coefficients. And they showed that the fluctuations could indeed lead to growth on the average. And Brandenburg and Vishniak also did a simulation with a zero mean alpha and showed that you could have a growth of the averaged field of what they would call an incoherent dynamo. So that was very encouraging. It was just the one simulation in that paper. Now, there was also a couple of papers by Slantiev, who he looked at alpha-omega dynamos with spatial dependence, which is what I want to do. His papers are very complicated, and I have to say, not very clear to me. But his principal result was you could get an extra alpha effect, which is due to the spatial variation in the fluctuations. That's true. But actually, there's another effect, which doesn't depend on spatial variation in the fluctuations, which he missed. I don't know quite how. So it makes sense then to look at this problem again. I'm not saying it's a new problem, but to try again and identify the important mechanisms, find a simpler ansatz perhaps than Slantiev, but also to apply the results to simple alpha-omega dynamo models to see what effect any new effect would have on those the evolution of mean fields. Yeah. So here's the maths. I know it's the end of the day. So we take a very simple problem, the simplest possible problem. We have an alpha-omega dynamo. Here's alpha, and here's omega. And the usual axisymmetric formulation. And of course it's almost illegible. But we imagine there are two time scales for alpha. Oh, alpha itself has a very short time scale. It has a mean, it's constant in time, and a fluctuating part which is large but varies on a short time scale. And the average of this fluctuating part is 0. So this incorporates both the usual alpha effect and a situation where alpha naught is 0, so there's only fluctuations. And this induces small changes in the toroidal field on the short time scale and order 1 changes in the potential on the same time scale. And for simplicity, we define this quantity alpha, which is the integral of alpha 1. So this is a quantity with 0 mean, whose derivative is alpha 1. And then we can simply, we have a small parameter, epsilon, and so we can simply write down the leading order equations. It's amazingly simple, and you get 2 equations for the fluctuating parts of A and B. So you can solve this one because B naught is not fluctuating, because then A1 is just gamma B naught. And then you solve this one because you know B1P, it's related to derivative of alpha 1. Sorry, derivative of A1. And you put those two together, and then you average this equation to get the mean part of A naught, and you get a new term, which is the quadratic this quadratic term averaged over the short time scale, which involves the fluctuating part of alpha and the fluctuating part of b. You can see the fluctuating part of alpha is large, the fluctuating part of b is small, and the average is of the same order as everything else. So it's all, you don't have to fiddle around with this too much. And when you work this out, using this formula, you get two terms. This is the term found by Solantiev, which you can see has the form of something times b naught. And he said, oh, this is an alpha effect, and it depends on the spatial variation of the fluctuations. Absolutely right. But actually, there's another term too, which doesn't depend on the spatial variation of the fluctuations, but does depend on the gradient of b naught. And he dismissed that, but it isn't dismissible because, in fact, even this term alone can lead to dynamo action.
Mike?
Yeah?
I'm sorry, this is a crucial point in your calculations. Could you please say me, you calculate this correlation function, this is instantaneous correlation function.
There's no correlations here, this is just a function of time.
Alpha.
It's something random in this. No correlations.
Okay, alpha 1 is taken at the time t, and b1 is taken at the same time t?
Yes, of course, at leading order that's correct. Because this only varies on the same... Yes, I've got two equations here. This does not depend on Tor, so you integrate this as though b naught was constant. This does not depend on Tor, so you integrate this as though b naught is omega is constant in time. This depends on Tor. So these are two simple equations you can integrate directly. All right? There's nothing random here. I'm just assuming this is some. There's no probability or correlation times or anything. If you like to think of epsilon as a correlation time, I'll let you do that. If it makes you feel better. Anyway, you get this term. And in fact, this is implicit in what Solantiev wrote down, but he just threw this away. But I think it's quite interesting. Now, if we want to get something different from the usual alpha effect, here's something different. Now, I've assumed here in a very simple way, I didn't think, perhaps I shouldn't have thought about it more carefully when I was solving this problem, but because I was thinking about the Hughes-Cattaneo calculations, I naturally thought of alpha as only a function of time, because that's what you see in their results. Of course, you could regard alpha as also a function of space and do a space-time decomposition. Then it isn't as simple as this, of course. You have to go into Fourier space, but instead of this quantity gamma squared, everything looks the same, in fact, except that you get an expression of this form where you imagine this bracket as meaning the integrals over k and omega. This is the leading order part. And you can see, interestingly, that the sign of this term is not necessarily, and I've got the sign, I'm sorry, this is wrong. There should be a minus sign in front of here, or in front of here. It should say minus gamma squared is this. Because this quantity is definitely positive. But this quantity can be positive or negative, depending on the importance of these two terms. And if I assume that omega squared is bigger than eta squared k to the fourth, which I certainly did here, I get a positive quantity. Whereas the other limit gives you a negative quantity. This is crucial, actually. If you change the sign of this term, it's not very good for dynamo action. Who are they shooting?
They got orders not to drill, and maybe they thought that it's now after 5 o'clock they can drill.
Yeah. They knew I was speaking. I realised actually, told them especially. I understand. I'll go soon. It's all right. No, didn't work. Oh. Okay, so a little bit more maths. So I just wanted to investigate what this term does. So here's an even simpler model here of a sort of Parker wave model in a periodic domain. And here is the new term, which involves a derivative of b with respect to x. Whereas the other alpha terms can all be subsumed into this one. You can see that omega prime appears twice, so the sign of the shear does not matter for this purpose. What does matter is that g squared is positive, which, if it's g squared, it's typically positive. But as I showed you on the last transparency, in principle you might want to replace this by something negative, in which case something different would happen. So you look for modal solutions which look like travelling waves, and for every solution with a given wave number in x, you get a dispersion relation which relates q squared, which is the scaled version of g squared, and d squared, the dynamo number, square of the dynamo number. So all these straight lines represent this curve here for a fixed m, and you can see that the new term enhances dynamo action. There's no dynamo action in here, but everywhere outside you have a growing mode for some m. So even when the dynamo number is 0, which I can't see very clearly, yes, even when the dynamo number is 0, you can have dynamo action when g squared is sufficiently large. But not when it's negative. This curve carries on for negative g squared down here, and so if this sign is changed, it impedes dynamo action rather than promotes it. So I tried to do something a little bit harder, not much harder, to think about timescales for cyclic dynamos of a very simple sort and the effect this new term would have on such cycle times. And so here I have a slightly more elaborate model, still one-dimensional in space, but now with the alpha term depending on x in principle, and with proper boundary conditions, say x is minus L and L. Say everything vanishes at x is minus L and L to simulate the two poles. And this alpha of x has two parts. Once you put in the new term, has an alpha term and a new term proportional to the derivative of b, and there's a simple quenching term just to control the nonlinearity. So you solve this between L and L. A and b are 0 at either end of the box, with alpha an odd function about the midpoint, and with a minus sign to get travelling towards the equator in the usual way, and everything else is a constant. So I take r to be a constant. It's consistent with the way that the new term appears that this should be an even function about the equator, whereas this should be odd. So it's perfectly natural to have this. If this were an odd function about the equator, then the solution would have no parity, which would be unnatural. So this maintains all the parity relations, but it has an effect. So these four pictures show you the effects of increasing r with positive r at fixed alpha, fixed everything else. And you can see here, this is the case with no r, usual dipolar sort of problem. You're looking at toroidal field contours. You have progression of activity towards the equator. Couldn't be simpler than this. Then you add a bit of r, and immediately the time scale goes up. So this period, in this direction, is much longer than this period. If you go on increasing, this looks the same as this, but it's not, because those with good eyes, which I don't have, will notice that this time scale here is quite different from this one. So this is compressed in the vertical, and this time scale is much longer than this. And finally, if r is too large, you get a steady dynamo instead of a periodic dynamo. So the effect of this new term is certainly to lengthen cycle times, if not to remove the cycle altogether in extreme cases. Well, it's a very simple model. So with the assistance of Paul Bushby, he used his model to look at the same thing. So these are now fully two-dimensional alpha omega dynamo models in a spherical shell with realistic differential rotation. Alpha is defined near the bottom of the convection zone. There is a sort of overshoot region where the diffusivity is smaller. This is all like his previous models, but now he's added a fluctuation term on the lines of the earlier slide. This is the base problem, the outturn for the toroidal field in his model without any of the new term. And then there are two different lines here, not so dissimilar. If you have, it's not quite clear how one should scale the fluctuation size. Depends what you think. And there are two extremes. One is you can think of the fluctuations as being proportional to the size of alpha or alpha squared itself. So when there's no alpha, there's smaller fluctuations. You could argue that at one level. More likely, you should probably think about a constant level of fluctuation. And there are some similarities between these. Again, you see the lengthening of the time scale here, followed by steady cyclic behavior. And here, you see, that looks very similar to that, but as you go on increasing the new term, you can see some steady wiggles here, wiggles in space, but not in time, and finally you get a steady solution here. This is turned into a quadrupole parity solution, but you can easily find a dipole one as well if you're looking for one. So those are the first simulations. I just have some more, which just came last night, actually, which is similar. only in black and white. And the difference here, these three are like the previous one. Actually, it's the same calculation as this bottom line here. But you're looking at the toroidal field below the base of the convection zone, where eta is smaller, and where alpha is smaller, and so the effects of the fluctuations are larger. So it is the same calculation, but it just looks more dramatic. You see these steady, space-dependent fluctuations, whereas here you have time dependence, and eventually the steady solutions take over completely. And here you have fluctuations are constant until you get to the bottom of the convection zone, and then they drop off rapidly below the convection zone, so you have now the level of fluctuation proportional to the magnetic diffusivity, just for a bit of variety. And again, that looks like that, but again you get these longer period things developing near the poles, and finally again you get a steady dynamo. So in all cases, you have a lengthening of the cycle time, followed by the end of the cycle. So this is a new effect, of course. Whether it's important in the sun is quite another matter. Who can say, but at least it's something you need to play with. So, points I want to make are, firstly, that this new term, fluctuating alpha effect, those two together, unlike in the Creighton case, give rise to a distinct dynamo mechanism. So it works even if there's no net alpha effect, in principle. Of course, David and I would like to have seen this in our simulations, and we haven't. So there's maybe a question mark here. Guaranteed, in some sense, to operate at large scales. The new mechanism favours steady dynamo action. That's quite important. It doesn't have any propagative effects, because it depends, in some sense, on the square of the differential rotation. Large-scale magnetic field generation may be possible even when the traditional alpha effect is ineffective. Well, I'd like to see real progress on that. David and I were hoping to make progress in this way. Sadly, we can only report that not yet. We haven't quite seen this effect at work yet. If we're trying to do fitting, many of us try and do this. We do numerical simulations and we try to fit the results to an alpha effect formalism. Maybe we should try instead to fit them to models involving the effects of fluctuation, so it gives you a bit more freedom to do that. And we need to do some more, which I've started to do. The first thing that one needs to be done, of course, is to work out whether the theory means anything, and I've looked at some early simulations with fluctuating alphas directly, without doing any averaging, and indeed you can show, just by numerical calculation, that the frequency of any cyclical behaviour does go down when the fluctuations go up. So that's support for the theory, but I haven't done enough to get the quantitative part of it right. And that's it. Thank you.
So it's good to hear that the magnetic fields the large-scale magnetic fields shouldn't be there in the observations.
Yeah.
Please.
Okay. In principle, for such model, you need to have two forcing. One forcing produces small-scale turbulence, and another forcing produces fluctuations of alpha. And this forcing should be separated in scale.
That would be helpful, of course, and that's why it's only an ansatz. Yes.
Otherwise, this model.
Of course.
So maybe it's possible to organize a numerical simulation. So.
I think one could do that. I mean, it would be a bit artificial, but it would be interesting to do.
Yeah.
In your numerical simulations, are you using the two-point correlation of the gammas or the alphas?
I simply use the formula. So it's just R, Bx. Okay, and on the which simulation? The one at the end. The last one. All I do is at every time step. The alpha, okay. So the term, I have a very simple alpha omega model. The one that, this one. No, not that one. That one. What I do is I integrate the equation without the R, but with alpha at every time step selected from some random variable with a certain mean.
What is the PDF of the random numbers which you choose?
Excuse me?
What is the probability distribution function? Is it a Gaussian or?
I think it was Gaussian, I can't remember.
Okay.
And I also multiply it by the square root of the time step. I've only done this, in the last few days. So all I know, and I can tell you, is that if you make this fluctuation big enough,
Yes.
even with zero mean, then you can get growth of mean field. And if you just add it to the constant alpha, then the original cyclical behavior becomes of lower frequency. So it mirrors what you have here from the ansatz. That's all I can say. Yeah.
1, 2, 3.
Two questions. One is in the first equation.
Yeah.
Your alpha function is independent of R, for instance.
I can't see what. Let there be light and there was darkness. So, what?
So your pattern is very weak. Is that correct?
The what is very weak?
Your alpha function is very weak.
Well,
So
it's a scaling. I could put any number I liked in front of the b squared. It means nothing. Yeah, it's a scaling for b.
And the other question is, when you have fluctuating alpha, would you also expect the fluctuation in eta?
Well, that's also possible, but I didn't, of course, include that. Yeah, somebody up there. Steve.
Transition to a study mode is homoclinic.
Well, my student is looking at this. It looks like, yes, it looks like the period gets longer and longer.
So if you use a different nonlinearity,
For example.
you might still get bigger.
Yes, but what I do know is that if you have no mean alpha effect, but only fluctuations, then you always get steady. Well, there's no mechanism for any propagation. The whole thing is symmetrical.
Even Paul's model.
I haven't tried that. But I can't see how... There's no directionality on any scale. I mean, I suppose in some general sense, yes, there's inhomogeneity between the pole and the equator, and that alone might be sufficient, but it's a very weak effect. I'd be very surprised. Very surprised.
First Kantos and you.
No, I just have a worry that when we assume alpha to be fluctuating,
Yes.
that maybe, like if you look at all those curves and you couldn't make out which direction the mean field is pointing, and it's just the electromotive force itself which is fluctuating. And
But the field is fixed in that case. That's the same. In that simulation, the Hughes-Catania simulation, B is a constant vector. It doesn't move. So the fluctuation in E is identical to the fluctuation in alpha.
But when you assume a form of the EMF to be alpha into B, then are you making more assumptions?
Well, all I can say about that, I take a point. I don't know if you can see this. Oh, God, sorry. All I can say that in this ansatz, I've lost the. All I can say is the fluctuating part of B is smaller than the mean part in this limit. And so I believe that I'm not making an error in assuming that B naught, on this short time scale, it can be considered a constant.
Yeah.
Okay, last question I would propose.
Regarding the question of Inyun's about the fluctuation of eta,
Yes.
indeed, the one of the components, eta 2,1, can lead to an incoherent
Yes.
shear current effect, which we
Yeah,
found
you
it does in
discussed
principle work, but it is less easily excitable by a factor of around 5 compared to the
Yes, no,
fluctuating
I'm
alpha.
afraid I simply didn't look at that.
I have to apologize, I forgot you.
Sorry, somebody. Oh, David.
But is there a problem with the actual convergence of the... I mean, you're assuming one of those averages is well defined. Yeah,
You had a problem with even finding an average, I know.
yeah, so you...
Well, of course, of course. I mean, yeah. I mean, in a real simulation, maybe this doesn't exist, so I can't answer that.
That's my argument.
Yes.
But that might be horrible.
Yeah, that's right. But I mean, these numerical simulations I did with very short correlation times did seem to lead to something reasonably coherent that makes sense.
I mean, be easy to check.
Yeah.
Okay. Thank you again. And we switch to the general discussion, which will be led by Andor.
Yes,
Right?
Marin, Gorky, and me here. So the idea is that I only here to irritate you, so that you discover other thing, right? So I'm here just to make provocative statements. And it was, during this day, there were at least 3 important points, including this point made by Mike, that whatever you expect, we are discussing turbulent systems, right? They must be noisy. They must be noisy. Then, at what level of noise and how this can be connected?
Yes.
I borrowed from how I switch to this stuff. No, on my USB. So, talking about noisy systems, right? And I think observers have realized it quite a long time ago that in order to see order in this noisy signal, you have to do something clever. If you just look at pictures, you will not see any order at all. For example, what Rainer showed today, the map of Faraday rotation measures in the galaxy M51. When the galaxy is observed with a high resolution, no, it's not CDs. USB-E, yes, E, this one, right? The low is JPEG is the bottom, yeah. Yes. This is the map of Faraday rotation measures, right? Faraday rotation measure is sensitive to the large-scale magnetic field. There's an integral, weighted integral of the magnetic field along the line of sight. So this is an integral across many turbulent cells. Well, of the order of 10 turbulent cells within this galaxy. And you see how strong are the fluctuations. So there are no numbers here, but we expected fluctuates from plus 100 to minus 100 radians per square meter, right? Something of that sort. Right. Even more. Meanwhile, the mean value that we expect from other considerations is of the order of what? Of the order of 100. Roughly the same value, right? 50, 30, but not 1. So, and then it's consistent with the idea that, for example, in the Milky Way, the observed estimates of the small-scale magnetic field squared divided by the large-scale magnetic field is larger than 1. It is the order of 3 or more. So what you expect is that the small-scale magnetic field is factor of 2, at least factor of 2 stronger than the large-scale field. And then obviously this result will depend on scale. This is true at very large scales where you average over a very large number of turbulent cells. If you look at smaller scales, you will see fantastically noisy picture. Yeah. And then David showed us today, stated that well, you have a system which is supposed to act as a dynamo, produce large-scale magnetic fields. You look at the energy, you see no evidence of the contribution of large-scale field to the energy. But David, with this factor, this ratio of energies, would you see the contribution of 10% clearly? Difference in 10% of helical and non-helical runs. So what should we do to convince ourselves that there is a large scale field in this picture? I guess that the picture you have is not noisier than this one. And still I know that Andrew Fletcher, and with Rainer together, after careful filtering, they found quite convincing large scale field in this picture. It is there. So what are the criteria?
It is very important also to compare here B large, the energy of the large scale magnetic field with the energy, with the turbulent kinetic energy.
No, but
and
if you,
this is a crucial point.
Yes, if you think that there is no occupantation, right?
Yeah.
Then this means that B squared is of the order of 4p rho V squared. That's it?
This is B squared.
Yes, but the contribution of the large scale field to energy is only, say, 20% at most. So if I plot well, there's nothing to plot, right? The large-scale magnetic field, the energies of the small-scale field alone and the total field. All differ by 20%. Still, we are talking about healthy large-scale dynamics, which we need to explain.
You want to say something?
I can add something to your arguments. We have, there is such a lady, Anna Khlestova from Irkutsk, and we investigated with her statistics of sunspots group which violates Hale polarity law. And it was possible to have quite a good statistics and so on, and basing on this statistic it is possible to insist that deep inside the convective zone you have the same kind of ratio between fluctuative and large-scale magnetic field. So this kind of estimate is typical not only for galaxies and galactic dynamo, but as well for solar dynamo. So now one can, with some care, argue that it is a generic feature of astrophysical dynamo. Such kind of ratio between.
So can we estimate? So can we estimate this theoretically from numerical or analytical models?
Analytical. We've got some analytical models with you, similar to your estimation.
What are the control parameters? Because we are, including me, I'm like a spoiled child. I'm used to mean field dynamo models which only have this and don't have anything else. Then, of course, this ratio is equal to 0 identically. And then I look at observations where it's larger than 1. And I start panicking.
Counterparameter.
But should I?
Ratio between this B capital and kinetic energy. It's a counterparameter. If it's order of 1 or less, say 20%, this amplification should be 3, 5, or maybe 10. But if you take very small magnetic field, I mean B capital, this amplification may be several tens or maybe 100. It depends on the Reynolds number.
Yeah, this one, if it depends on Reynolds number, then getting for the 1 will be very difficult.
It's possible that the B
less
than, say, Reynolds in 0.25 power minus.
All right, to the power of 1/4.
1/1, minus.
It's 1,000.
No.
It will easily be 1,000.
Minus. B.
It will be 10 to the minus 1,000.
Yeah.
I want to put something for the 1. 2 or 3.
B capital. In this case, the amplification will be logarithm of Reynolds with some coefficients.
I just wanted to remark that I don't think there's a problem with what he was showing. But he showed you the spectrum which clearly indicates that there is no large-scale field. I think that you have to be no problem.
There is no large-scale field.
No, because the spectrum showed, right? The power went down smoothly, so.
It was going down,
yes. Unless you want to do a wavelength or something else, if you are just happy with Fourier space, then there is no large scale. Okay, why it is not there is a different question, but at least it was clear, I think, in this figure. But
sorry.
Okay, I would still like to ask, maybe what I mean, the simple kind of 1D model which Sharanya was playing with, this fluctuating pitch here, you need to go to much larger kind of time numbers so that you start going with this. So I don't know whether it's...
I'm sorry, you are distracted. I'm sorry. Start again, quickly.
In the simple models which...
For small magnetic field.
You need to go to
for small, B less than... yes.
Perhaps, yes. And I've got nothing to say about partition.
This is the whole thing. No, it's already partition, basically. B much less than the partition field.
This is what you're saying, right?
If B much less than B capital,
much
less than
this.
Yes, right. And we know criteria.
Steve.
You asked the question before, should you start panicking?
Mm-hmm.
I mean, there's no need to patent it. You just have to think, David's results, if you believe in mean field electrodynamics and all its, that it is the answer, then you do have to explain why David gets the results he does. Now, you don't have to panic because you know that the natural world, whatever, does what it does. So the sun, you can work out, it does have a large-scale field. And it has it ratios to whatever it is. And the galaxy, you say the same thing. But then you might have to say, well, can we believe the theory, apply it to this and the sun, if it doesn't explain David's simulations? And if you say, yes, we can, then you have to explain why David's simulations show what they do. And it's not a matter of panicking. You think, okay, this theory might not work. Let's just think of some other theory.
But with this estimate, which Nathan points out, and so it would be important to suggest for some to interpret the results Rainer is showing, the results which come from observations, and there will be more results like this, because now radio observations of galaxies already have achieved the angular resolution of them, have achieved the resolution comparable to the energy range scale of turbines. Within a few years, there will be further improvement, right? And the resolution will be significantly higher. So people will start observing in the spectrum of turbines, so at the beginning of it, large-scale part of it, in the interstellar medium. So, and then the value of simple estimates like that will grow. So, is it an acceptable estimate? Any opinions? If yes, then I put point here and I start using it in my own work.
What is acceptable?
Let's hope. Okay, wait.
How obviously this ratio should depend on the magnetic Reynolds number. The only way for it to be not very different from 1 is if it depends on a logarithm of Reynolds number. Otherwise, there is no other way to have it.
Right.
Like that.
So, for large magnetic field, much larger than a partition, I mean a capital, B capital, it tends to 0 simple according to our estimation, this ratio. Because the B square tends to equipartition, B small. And as a result, this ratio tends to 0 when B capital tends to infinity.
But not your missing. I mean, the whole debate is whether capital B can actually grow to even this much, right? I mean, you're not worried whether there's log there or something there, but you're worried whether there's 10 to the 18 there or
I didn't dare suggest that this is discussed now. The role of magneticity and its fluxes. Do you want to discuss it now, David?
No, I don't want to discuss that. But the problem as I see it is that you can do mean field theory and you can work out what you think alpha is and you can work out what you think beta is, and that produces good. But that is not what you see, because there is another object which is small scale dynamo whose growth depends on all kinds of different things like Lyapunov exponents, cancellation exponents, which are completely from a completely different zoo. But that's what you see. And so, yeah, maybe hidden underneath all of that big zooey thing is a large scale field, and you go, what the heck? I never see it. I'm swamped by this thing. Then you go, I'll come along with some of this thing, and you just change the small scale dynamo in some way. And so, I think that's, well, to my mind, that's the problem which I find hard to get around. High enough power. I can see ways around astronomical objects how they might do it. You can drive dynamos either in completely different regimes where the field is strong enough to alter the convection, for example, or where you close the dynamo loop through instabilities, for example. There's ways around it, and I think maybe they should not, they're worth looking at. But I think in terms of the classical driving a dynamo through small-scale helical convection or helical turbines, I think there's a problem.
I think I agree. The only way you can get around that problem is if there's some parameter which affects the small-scale dynamo in a different way to the large-scale dynamo. And the only one I can think of is the magnetic parameter.
Well, I think the difference in galaxies is that there are, well, strong helicity fluxes, not only the one which Nathan was talking. It's an open system. Galactic disk, unlike the Sun, is an open system. There is a constant exchange of matter and everything you want between the disk and the surrounding medium in the halo.
So that's understanding you have a huge magnetic function,
Yeah.
which really, you get structures on really fine, magnetic structures on really fine scales.
Well, I don't think that they are measured in centimeters, those scales.
Oh, okay, then you have to think how you get them out.
Yeah, but there are also, I mean, see, if you want to worry about the galactic kind of case, and you want to give up on the dynamo, okay, then you would think, can you do it with fields produced in the early universe or some primordial fields? And it's not easy either, because those scenarios, and of course, given the uncertain physics, no scenario without tuning a parameter exponentially finely can produce a field which is required to be just flux frozen and make a microgauss galactic field. So,
but you mean kind of in the early universe?
Yeah.
But I can still get away from these arguments by suggesting some intermediate stage that these pre-galactic fields are formed, for example, in the proto-galaxy.
yeah, but then you have to order it in the proto-galaxy. Okay. Somewhere you have to order it. And the easiest place to order it is in very early universe where you stretch everything to very large scales. Okay, and so having looked at that thing, so you have to decide which problem is worse. You want to solve that problem, which is also difficult, or you want to solve the problem here. And I don't think either of them have a solution at present. So there is really no alternative which is fantastically bad for the dynamo also. So even though, of course, for the Sun it's more obvious because things are changing periodically and then you have to do it and you are not going to freeze in a field and then let it go. But what I think is worth doing, and maybe other people can look at it, is to start from finite strength fields. Because we do know that even if you just leave a field there, it will decay because of all the motion. But if you already start with a large enough field to be dynamically important, large enough ordered field, what happens to that, I don't know. And that could be a worth thing to check.
I guess Zildovich many years ago answered on this question.
Sorry?
Zildovich many years ago answered on this question. What will we start very strong magnetic field? This field simply disappeared to the level which is acceptable in order to produce normal dynamo. Remember this estimation?
It can be a different branch completely. It doesn't have to be joined to the kinematic branch. It can live up there of its own volition.
Yeah, it can be entirely different. Yes, entirely different solutions.
Is it always possible to separate it large and small scales? I mean, this arm structure, right? So it's long and it's thin. So in Fourier space, it will have a spectrum all across. And it's
Yes, it will.
structure, right? So it's part of the same. So
I think numerical simulations, for example, systematically, with the Reynolds numbers available, they very rarely show these two peaks in the spectrum. It's always one peak and then some extension to smaller scales, right?
No, I mean, as far as the poloidal magnetic field is concerned, there must be a certain scale, and that scale should be smaller than the scale of the system. So, in other words,
so on this picture, would the thickness of the arm?
yes, in the vertical direction,
Small or large scale?
that would be the small scale.
No, the thickness of the arm, it's 10 times larger than the energy range scale of turbulence.
No, I mean, in the conservative sense, it would be 100 parsecs, the thickness of the arm.
No, 1,000.
But as far as the magnetic field is concerned, you're talking about the magnetic field thickness, the magnetic scale height. Are you not? Sorry.
No, this thickness of the arms, let's make it dimmer,
No, I mean,
but so that we can see each other.
Thickness across the plane.
This scale here, the thickness of this feature, this scale, is what? 10 times, 15 times the energy range scale of turbulence. right? Thickness of the arm is about 1.5, 2 perhaps kiloparsecs at most. Or maybe even 1 kiloparsec, right? And Rainer should know this by heart. About 1, right? So 10 energy range scales here. But the galaxy, we see it almost face on, so it's also only 10 turbulent cells along the line of sight.
So it's not very well separated?
Oh, it's not, yes, it's not. 10, you should be very lucky if you have just an expression of 10. Yep.
Sorry, you mentioned characteristic turbulent scale. But how do you know that? What?
I guess. Because the real observations are, of course, available only in the Milky Way to some extent. Again, they are not very conclusive. So it can be 50 parsecs. It can be 150 parsecs. Again, it's one of the parameters which is not very firmly known even for the Milky Way. And here I'm just using the same value as in the Milky Way. I'm just doing something which most often people prefer not to do.
Before I thought about, she had some observations of the turbulent cells or scale, the rotation measure. You had the recent paper on.
Yes, I'm sorry. I got lost quite some time ago, so sorry.
No, you had some observational evidence, measure of the correlation scale of the field or something,
Yes.
right? From observations. It was even less than 100, it was a few parsecs or something like that.
That was a difference between spiral arms and inverter regions
Right.
from structural point of external distortions. And in the spiral arms, the maximum scale that we observe is about 50 parsecs, whereas in the inverter regions, it's
100 parsecs.
well, very roughly, but at least much, much larger.
Rough, but seems to be reasonable estimate. Rough, but reasonable.
Let me jump from observation to experiment. We observe in our laboratory large-scale convection. I mean, we observe we build some box and we produce very nice convective cells in large scales. But for us, it was very big surprise that the small-scale stuff had very nice scale separation, less than 10, but say 6 or 7. So if our large-scale cell was, say, 23 centimeter on 56, and our eddies, small turbulent eddies, real eddies, were maybe maximum 3.5 centimeters. So I believe that if we've got pronounced structure, and in other words, it means that we've got good scale separation.
Any more grievances?
Maybe we should summarize briefly, because there were some parts which I missed, unfortunately. And maybe that's summarizing conclusion would be useful for others as well, of course.
Oh dear.
No?
I don't think you can summarize.
No, I cannot.
Yes, naive question. So one looks at a picture like this and starts to argue, oh, this is an A0, S1, or whatever dynamo. Shouldn't be many of the simulations be transferred to data space and compared there?
Yes, exactly.
Because all the degrading of information in the process of radiative transfer to us and our observation and our data reduction changes what we are seeing, changes information, and as Rainer said, it would be important to have more synthetic observations because trying to extract something directly from a map and being sure that what you have extracted is not just some observational noise is very hard. So my question to the community of people simulating dynamos, trying to simulate dynamos, is it already this state-of-the-art far enough evolved that they can produce synthetic observations and claim, well, this is how your galaxy should be, or should we wait a few few more years before simulations are advanced enough in order to be compared to real observations.
So, any opinions?
Yeah. We don't understand miles away.
But how you know they don't understand it before you compare to them with the results of the observations?
Oh,
how you know that you don't
if
understand
there's no
them?
magnetic field?
We can't make predictions about the simplest systems that we can study numerics.
But
Okay, so you're saying that even given some very simple physical system, different people come to very different conclusions of how it will evolve.
Yes, that's right.
Depending on the scheme of observations they're using.
I know, yeah. There's no agreement, I would say, on quite simple numerical systems that people study.
And if this is so today, it must have been in the past for a long time, and how long in the future will it be the case?
It was easier in the past because you couldn't actually test the theories.
It's getting worse.
Yes.
Right.
But if you then go from the models to the real, to the observable maps to compare the observations, then you're facing new problems.
Yes.
So if you go, for instance, to the synchrotron, then we had this discussion, Anwar and David Master, what is the distribution of cosmic ray electrons? This is also quite largely uncertain. So what is their diffusion length? How well are they correlated to the field? So are they smooth within the galaxy or not? Depending on the assumptions that we know very little about, the radio maps, they differ completely. Or in the case of this new field map of Solomon and Torsten and Vedel, it depends crucially on the distribution of thermal electrons if you want to explain the Faraday rotation. And there's only one standard model of the thermal electrons in our galaxy, which is by Cordes and Lazio, and this is strongly debated. There may be severe problems with this model. So if you change the model, which is not known at all, then the distribution of the rotation measures changes completely. On the other way around, so your comparison observation just depends on many unknowns. So I think we are still very far from doing detailed observations.
But nevertheless, I won't be. May I just say, Torsten, before I pass it to you, because still we shouldn't be pessimistic, because we are not the only people in the world who are in the same situation, who don't have complete and perfect theories. Complete and perfect theory will mean the end of this business,
yes,
of our community, right?
Yes, of science.
In this sense, it's natural that we shall never have perfect models. Still, it is important to isolate those features of those imperfect models that we have, which deserve comparison and can be compared with observations. The work we did with Rainer, for example, I was amazed. I thought that we shall have a good model for the flow in a barred galaxy. We shall have excellent observations from Rainer of barred galaxies. Just compare the two. I was amazed to see that it's not true what exactly you will compare in your model with what taken from observations. I was amazed. It took 2 years for us just to isolate those parameters which can be meaningfully compared. Because what you first think will be comparable energy densities. Oh no, we don't have good nonlinear model. Energy densities cannot be compared. Okay, Faraday rotation measures. No, we don't have a good model for thermal electron distribution, and so on and so on. But still, we have to find a way to compare models with observations, both in imperfect observations with imperfect models. And I think that it's important, but there are not many achievements in that direction. Probably it's important in meetings like this also to think about this. Torsten.
Yeah, I want to just push in the same direction. So if you have, for the same physical model system, different description giving different prediction, the answer has to come from the observation until you manage to agree on what the right description is for the level of simplification. And in that case, you can't avoid to start to look into the data and try to extract properties of your models which might be found again in the observation, have survived this observational process.
In this uncertain situation, that it's very difficult to compare theory with observation, I totally agree with Dave. We should find something simple and study very carefully. But no, not always simple. Always simple, it's important too. Because we know for sure that for galaxies it's very important open system, and say magnetic field can penetrate fastly in hollow, for example. So in periodic system, periodic box, we've got very specific situation which not so similar to a real situation in nature. And we should organize something in order to resolve this reality. I guess the reason why you have normal generation.
Sorry, my connection was
Yes, okay. I just want to ask a completely different question. First, I just want to ask a question. Is it at all thought that the structure of these galaxies that you see is affected by the magnetic field? Or is the magnetic field essentially passive in determining the light structure?
If you talk to people in galaxy formation, they ignore magnetic fields and cosmic rays completely.
Okay.
And they are happy since they can describe everything. I'm not saying that they are right.
No, but they don't find an inconsistency. Yeah. So the question is,
well,
what I was going to continue to say is that so many of our theoretical studies are based on periodic boundary conditions, uniform, this and that. This is not very uniform, and it may be that one needs a slightly different approach when actually the background is so inhomogeneous.
Oh, this is only part of the story. As you remember, if you go to the other two dimensions of the magnetic field, it's very homogeneous and extremely smooth.
Yes.
So this shows only one field color.
Yes. Okay, no, I understand.
The other one is very smooth. So this is this is also giving the argument also with the polarization factors. It must be the magnetic field. So there's no way out. And this evolution people, they just cannot explain any magnetic spiral. So the field is there. So
okay.
And this is
just a hope.
and this is a large scale field.
What do you mean large scale? You cannot tell the telescope, don't only observe large scale field, right?
No,
For the rotation, it is large scale, more or less.
No, any field will produce finite radio rotation. It will decrease, increase like square root of n. Even a random field will produce random radio rotation, right? This is why you don't know. You don't know.
No, but M31 is another large scale.
Yeah, you said one. You have.
I was just wondering, because I always believed that the measured energy density in magnetic field is much lower than the turbulent energy density and much lower than the kinetic energy due to rotation.
Yes.
So there cannot be a great effect of magnetic field on the overall spiral structure formation of the galaxy.
But there are still subtle effects which can make it. For example, Ryan mentioned it, that somehow magnetic, in the shock waves, because these are spiral shocks there here. And there are other examples in barred galaxies of large-scale shocks where the gas density is compressed by a factor of few tenths, and magnetic field is not. This almost by definition means that magnetic field affects the compression of the gas. There are some ideas how it can happen. It's a very non-trivial thing. It means that there can be subtle effects of magnetic field, or the diffused, perhaps, gas. Not of the total, because much of this mass is in stars and molecular clouds. Diffused gas can have much smaller energy density. And in addition, when you talk about the rotational energy, the overall rotation is unimportant. The velocity shear is important in streaming motions, which are a factor of 10 weaker than the overall velocity of 200 kilometers per second. So magnetic field doesn't care about 200 kilometers per second. It cares about the small local differences, small local shear, which is a factor of 10 smaller. Steve.
I want to come back to this kind of philosophical issue about how far you should try and get your theory to agree with observation. I think everybody has their own threshold where you say, come on guys, you're really pushing the theory too far. But I think it is important to take a theory and try and work out what is robust in the theory, what doesn't change whatever you change, whatever you do, something doesn't change. Something there's a result which is generic to all models. If you can reduce it to the simplest possible model and that result is still there, then maybe you can take something away. If you don't understand the nature of alpha, then there might still be something you can take out. But I think that this threshold that people have is very person dependent. now what am I learning? And I'm not
But
learning
this,
anything.
one of
look for things that are generic.
this was one of the reasons, for example, why I was, well, somehow thought that it's not much point in comparing in detail nonlinear dynamo models based on alpha quenching with galaxies, just because there is, well, they are always in play. But now, with these helicity fluxes, where if nonlinearity is due to helicity fluxes, then immediately the models become much more rich in terms of physical content. And then you can test the models by comparison with observations. For example, one of the predictions which you can make, it will be that the star you can relate magnetic field to star formation rate, because star formation rate controls the exchange between the disk and the halo in everything, including that. So this is a testable prediction. This you can test and say, is it what you observe or no? If you're not, if you're unlucky, again, you will be in the impasse in between the two. Yeah, but if you're
in some ways, this is a nice effect of what Dimitri was saying. I mean, his talk, he relies just on the symmetries of, doing things in a full sphere versus doing things in a spherical shell. You can show that there are differences there that you might expect. Even if you do not understand anything to do with the alpha phase, you might expect something to. So I think that's a nice point. It's just, I'd like to say it's not a personal choice.
Regarding the relative importance of magnetic energy and kinetic energy at different scales, Thorsten showed a plot where you showed the two spectra, and the magnetic spectrum had a peak which was shifted to the smaller scales, and he supported this supported with this observation, with this suggestion, Kandu's theory. Now, the one thing that perhaps unconsciously also took place, that you shifted actually downwards the spectrum towards smaller energies, suggesting therefore that at all scales the magnetic energy is actually below the kinetic energy. So what is then the expectation? Should it be below, should it be equal, or should it be above? And the simulations that we have had so far is that it should actually be above.
Sometimes.
Say again?
This is a non-helical environment. There's no.
I'm also talking about non-helical, yes. Non-helical, yes.
Yeah, but there's also simulations of non-helical. But actually, the total magnetic energy is less than the kinetic energy in the simulation.
Yes.
That's what he's saying also, I think.
Yeah, but the spectrum was also, in your case, at all scales below.
Well, the hydrodynamic spectrum was not measured.
No. But no, that's why I was saying it was unconsciously done.
Well,
because you just assumed something.
It was just it was illustrating Kandu's theory.
No, I mean, theory is too much, but if you had a sharp cutoff in the velocity, which is for high Prandtl number, that's what. Then of course you will get some excess magnetic energy over the kinetic energy in the spectrum. But he was just having Kolmogorov in both places.
I'm talking.
In which case you are getting that will be equal like that.
No,
right?
above.
Above.
Magnetic is above, yeah.
Right, and this is what Reiner argues in this case of galaxy 6946, that there is some evidence if you do more or less standard operations, the conclusion is that magnetic field is a superior partition in large parts of this galaxy.
I see.
I was always arguing with Reiner against this, but here's the point. So then what's the status of supercompetition fields? Well, can I put it naively? Well, I always thought that, okay, fine, it's only for generic magnetic field. B squared is a measure of magnetic force. If the field is almost force-free, it can be arbitrarily strong, right? Still, the Lorentz force will be small. So what's the meaning of a competition with kinetic energy? How it depends on the topology and geometry of magnetic field. Is it feasible, is it thinkable that we shall have super competition magnetic fields everywhere above kinetic energy or not? But, for example, your mechanism it immediately gives you why it is super competition? Why the Lorentz force?
Because the shear is supplying a large amount of energy to the magnetic field. You're not limited by what the turbulence has to supply.
So this is kinetic turbulence is like driving belt, right? It only transfers energy from one source, from the source to the goal. It just will transfer as much as you want, even if slowly, right?
Well, I mean, of course, there are limits, but they come from other things.
So, is it a sacred cow? Equipartition with kinetic energy, or we can just dump it? Is it easy or is it not? Why? So what you need to
You
have
have to locate all the sources of the kinetic energy. In this case, it's also rotation. So you can't exceed the rotational energy.
Oh yeah, no. Nobody thinks about exceeding rotational energy, right? And the rotational energy, perhaps we should also live in peace. Turbulent energy.
By the way, the equipartition is sacred cow in astrophysics only. People in geodynamo suppose that the magnetic field can be highly super equipartition without any care. And consider it as completely standard idea.
Should we follow the example and forget about any care and keep going? So, but what are the am I wrong saying that superrotation is easy to dispense of just because magnetic field can be locally force-free, helical? We are talking about helical fields, right? But almost partly by definition, helical field means the Lorentz force is much smaller than b squared divided by the scale. Is it enough or is it not?
But nothing is fully.
It's really enough. Welcome first. Well done.
Just a question about this super equipartition fields. What's the scale of these fields compared to, spatial scale of these fields compared to the kinetic energy?
The scale
Are they
is...
the same scales or spatially?
Which
If this is K, here we plot the energies, right?
Then magnetic, kinetic energy goes like this. Magnetic energy goes like this, and then I should stop. And it's possible that the two converge, of course, but that's not clear really. So as far as the simulations show so far, they stay like this.
And perhaps what Reiner argues for, that even the total energy integrated over the spectrum in magnetic field can be larger.
That's connected with the that's at 6 o'clock.
Yeah.
I mean, they're building a highway underneath here, right? And this takes several years, of course. And of course, they got orders not to blast and not to drill while the lecture's on. But of course, they think after 5 o'clock the road is free. Of course.
Possibilities is all.
That's.
Are they going to destroy the building?
They're 7 meters below us.
I feel a lot safer in a bar.
Yes. So, yes, Rita. Yeah.
What's the scale of separation?
No, it's about super-equipartition. What Axel says that the magnetic energy density is larger than kinetic energy density at smaller scales.
Yes.
Yeah.
But probably if you integrate, you still have equipartition between total kinetic energy and total magnetic energy, right?
There's less magnetic energy.
More magnetic energy will be less.
Normally less.
Just because the filling factor of because the spectrum doesn't tell all the truth.
Yeah.
Because magnetic field is intermittent, so the phases are not random. The filling factor is much less than 1 in magnetic field here. It's intense, but it's localized. But what Reiner says, that observationally, again, I won't say, Reiner probably would agree that the arguments in favor of super-equipartition fields are not absolutely Arab custom.
And don't say that the total field magnetic energy exceeds that. I said the outer part seems to exceed. The inner part both agree. The further out you go, the more the magnetic field seems to dominate. Maybe because the shear gets stronger and stronger towards the outer part, or MRI or anything else. And of course, many of these things can be discussed. So the equipartition argument, of course, because many things are uncertain, but this tendency is relatively strong and stable.
Can I suggest that we now make 3 more comments, and then white wine is getting warm there, and red wine is getting cold. Simultaneously. Both are getting warm.
Which equipartition before we
And then
I guess that all this stuff about equipartition more is actual for small scale magnetic field. For large-scale magnetic field, yeah, we know from geodynamo, it may be not so actual. If we speak about super equipartition, we speak about large-scale magnetic field.
Two more comments, please.
Let's go.
Two more comments, one.
Let's
Two more comments, two. Wine party. Thank you.